In this screencast, we're going to go through an example where we solve material balances involving multiple reactions using the extent of reaction method. Now, what is the extent of reaction? We write it as psi. It has units of moles, and we could use it with reactions to determine the extent at which the reaction proceeds. Now let's look at our general definition for our material balance, in which we have no accumulation, where we say in plus generation minus consumption is what comes out. Now, if we write this as the moles out of a reactor are equal to the moles in, and we group the generation and consumption terms into one term, it gives us an idea of how many reactions have occurred, then we could write this using the stoichiometric coefficient of each species times the extent of reaction. So let's take a quick look at a very simple reaction, A going to 2B, where we could write this as the moles of A out of a reactor are going to be equal to the moles of A that we start with, and it's going to be plus or minus, depending on what side of the equation we're on, and since we're consuming A, we're going to subtract out 1 mole for every reaction that occurs on a molar basis. For B, same initial setup, but now we're generating 2 B molecules for every A molecule that has reacted. So now we've used the extent of reaction to write 2 material balances for both A and B. Now let's take a look at the problem at hand. So the following problem says we have 100 moles of ethane that are sent to a reactor to react to form ethylene and hydrogen gas. However, a side reaction occurs in which ethylene reacts with ethane to form propylene and methane. Now we're told that the fractional conversion of ethane is 0.7, and the selectivity of ethylene to propylene is 5. And the goal is to find the composition of the product gas. So with any material and energy balance problem, we should start by drawing a figure. So here I have my reactor with both reactions in it, and we know that some amount of ethane comes in, 100 moles, and leaves as a product stream. And we're asked to determine the composition of that product stream. So we need to finish labeling our system by putting in our unknowns. We should also write in our fractional conversion, since it's given to us, and our selectivity of ethylene to propylene, and that's given as 5. So we have all our information that we've been given in the statement, and we have all the information that we need to find labeled. So the next logical step is to do a degree of freedom analysis to make sure that we're not missing anything. So for our degree of freedom analysis, we start with our unknowns, which we have 5 of. We add the amount of independent reactions. We have 2 reactions. We subtract out the number of molecular species, and you can see from our 2 reactions we have 5 species. And we subtract out any other pieces of information that could help us solve our problem, and we have selectivity in our fractional conversion. When we add the first 2 up, subtract the bottom 2, we have a degree of freedom analysis that gives us 0, which means that it is solvable, as is. So we've written all our unknowns and our knowns, and we can move on. So let's start by using our fractional conversion, which says that value of 0.7 is going to be the amount that has converted from what's come in to what's come out into our reactions. So we could write this by saying that what goes in to our reactor minus what leaves the reactor divided by what went into the reactor is equal to the 0.7. And our selectivity tells us the ratio of the amount of moles of C2H4 to the undesired product propylene. So those are our 2 pieces of information we're going to use with our extent of reaction equations. And we can use the extent of reaction, as you recall, where we write the amount of moles leaving the reactor for our first product. That's going to be equal to the amount that originally went in. We designate that with a 0 at the bottom. And we're going to subtract out the external reaction for reaction 1, since for every reaction that occurs we lose 1 mole. And since it reacts in reaction 2, we're going to subtract out the extent of reaction 2. And that would be our first equation. Now we repeat this for our other product. Write it as what came in. And since we're producing it in the first reaction, We write it as a plus, and we're using it in the second reaction, or consuming it. So we subtract out the extended reaction 2. Now I'm going to continue this for the other 3 species, and we have our 5 balances for our 5 species. So you could count the amount of unknowns that we have. So we have 1 unknown here, 2, 3, 4, 5. And then our extended reaction for the first reaction and the second reaction are unknown. But we know what is entering our system. That's given in the problem statement. And we know that that's the only thing entering. So we could get rid of this term. So we're down to 7 unknowns, 5 reaction equations, and 2 pieces of information we have above it. So we can move on to solve. We can take our first equation and substitute in what we know here, which is that we had 100 moles entering our process. And we know that that was the only thing entering, so this should go away. So we can start solving based on the information that we have. You can see that this is the only we have to solve for using our fractional conversion. So solving for the moles leaving, we get 30, and plug that in here. I could also rearrange the first equation so it looks like the following. We could use our selectivity and plug in our equations, which would be equation 2 and equation 4, into our selectivity equation. Doing so looks like the following. Now we could use that equation to have a relationship between the extended reaction 1 and the extended reaction 2. And we can see that the extended reaction 1 is equal to 6 times that of reaction 2. We're going to plug this information into equation 1. Solve for the extended reaction 2 equaling 10 moles. And using what we had before, extended reaction 1 is equal to 60 moles. So we've solved for both our extended reactions, and we can plug that information into our 5 equations you see here. So now we could solve for all of our unknowns. Hopefully you get the same values I got. Since the question was asking what the product composition would be, at this point we would need to determine the molar fractions of each component. We could add up all of these and we get a total amount of moles of 160. Now to solve for each of the molar fractions, which we'll designate as Y, just the amount of moles of the species we're interested in divided by the total amount. So here I've written out the molar fractions of each of the components, and a good thing to do is check that they add up to 1. So hopefully you can see through this video how to use the extended reaction to calculate for unknowns in a material balance involving multiple reactions. And as you can see, the more reactions we have, the more complicated the problem gets as you introduce a new variable for each reaction.